probably talking about data with just one of the three V's from big data. So either volume or velocity or variety, but singly. So for instance, genetics data, you have a huge amount of data and it comes in a very set structure and it tends to come in at once. So you got a lot of volume and it's a very challenging thing to work with. You have to use data science, but it may or may not count as big data. Similarly, streaming sensor data, where you have data coming in very quickly, but you're not necessarily saving it. You're just looking at these windows in it. That's a lot of velocity and it's difficult to deal with. It takes data science, the full skill set, but it may not require big data per se. Or facial recognition, where you have enormous variety in the data because you're getting photos or videos that are coming in. Again, very difficult to deal with, requires a lot of ingenuity and creativity, may or may not count as big data depending on how much of a stickler you are about definitions. Now, if you want to combine the two, we can talk about big data science. And in that case, we're looking right here at the middle. This is a situation where you have volume and velocity and variety in your data. And truthfully, if you have the three of those, you are going to need the full data science skill set. You're going to need coding and statistics and math, and you're going to have domain expertise, primarily because of the variety you're dealing with. But taken all together, you do have to have all of it. So in sum, here's what we get. Big data is not identical to data science. Now there's common ground. And a lot of people who are good at big data are good at data science and vice versa, but they are conceptually distinct. On the other hand, there is the shared middle ground of big data science that unifies the two separate fields. Another important contrast you can make in trying to understand data science is to compare it with coding or computer programming. Now, this is where you're trying to work with a machine and you're trying to talk to that machine to get it to do things. In one sense, you can think of coding as just giving task instructions, how to do something, and it's a lot like a recipe when you're cooking. You get some sort of user input or other input, and then maybe you have if-then logic and you get output from it. To take an extremely simple example, if you're programming in Python version 2, you write print and then in quotes, hello world, and that will put the words hello world on the screen. So you gave it some instructions and it gave you some output. Very simple programming. Now, coding and data gets a little more complicated. So for instance, there's word counts where you take a book or a whole collection of books, you take the words and you count how many there are in there. Now, this is a conceptually simple task, and domain expertise and really math and statistics are not vital, but to make valid inferences and generalizations in the face of variability and uncertainty in the data, you need statistics. And by extension, you need data science. It might help to compare the two by looking at the tools of the respective trades. So for instance, there are tools for coding or generic computer programming, and there are tools that are specific to data science. So what I have right here is a list from the IEEE of the top 10 programming languages in 2015. And it starts at Java and C and goes down to Shell. And some of these are also used for data science. So for instance, Python and R and SQL are used for data science. But the other ones aren't major ones in data science. So let's in fact take a look at a different list of most popular tools for data science. And you see that things move around a little bit. Now R's at the top, SQL's there, Python's there. But for me, what's the most interesting on this list is that Excel is number 5, which would never be considered programming per se, but is in fact a very important tool for data science. And that's one of the ways that we can compare and contrast computer programming with data science. In sum, we can say this: data science is not equal to coding. They're different things. On the other hand, they share some of the tools and they share some practices, specifically when coding for data. On the other hand, there is one very big difference, and that's statistics. Statistical ability is one of the major separators between general purpose programming and data science programming. When we talk about data science and we're contrasting it with some fields, another field that a lot of people get confused and think they're the same thing is data science and statistics. Now, I'll tell you, there's a lot in common, but we can talk a little bit about the different focuses of each. And we also get into the issue of sort of definitionalism, that data science is different because we define it differently, even when there's an awful lot in common between the two. It helps to take a look at some of the things that go on in each field. So let's start here about statistics. Put a little circle here and we'll put data science. And to borrow a term from Stephen Jay Gould, we can call these non-overlapping magisteria, or NOMA. So you think of them as separate fields that are sovereign unto themselves with nothing to do with each other. But that doesn't seem right. And part of that is if we go back to the data science Venn diagram, statistics is one part of it. There it is in the top corner. So now what do we do? What's the relationship? So it doesn't make sense to say these are totally separate areas. Maybe data science and statistics, because they share procedures, maybe data science is a subset or a specialty of statistics, more like this. But if data science were just a subset or specialty within statistics, then it would follow that all data scientists would first be statisticians. And interestingly, that's just not so. Say, for instance, we take a look at the data science stars, the superstars in the field. We go to a rather intimidating article. It's called The World's 7 Most Powerful Data Scientists from Forbes.com. And you can see the article if you go to this URL. There's actually more than 7 people on the list because sometimes he brings them up in pairs, but let's check their degrees, see what their academic training is in. If we take all the people on this list, we have 5 degrees in computer science, 3 in math, 2 in engineering, and 1 each in biology, economics, law, speech pathology, and 1 in statistics. And so that tells us, of course, that these major people in data science are not trained as statisticians. Only one of them has formal training in that. So that gets us to the next question. Where do these two fields, statistics and data science, diverge? Because they seem like they should have a lot in common, but they don't have a lot in training. And specifically, we can look at the training. Most data scientists are not trained formally as statisticians. Also, in practice, things like machine learning and big data, which are central to data science, are not shared generally with most of statistics. And so they have separate domains there. And then there's the really important issue of context. Data scientists tend to work in different settings than statisticians. Specifically, data scientists very often work in commercial settings where they're trying to get recommendation engines or ways of developing a product that will make them money. So maybe instead of having data science as a subset of statistics, we can think of it more as these two fields have different niches. They both analyze data, but they do different things in different ways. So maybe it's fair to say they overlap. They both have analysis in common of data, but otherwise they are ecologically distinct. So in sum, what we can say here is that data science and statistics both use data and they analyze it, but the people in each tend to come from different backgrounds and they tend to function with different goals and contexts, and in that way render them to be conceptually distinct fields despite the apparent overlap. As we work to get a grasp on data science, there's one more contrast I want to make explicitly, and that's between data science and business intelligence, or BI. The idea here is that business intelligence is data in real life. It's very, very applied stuff. The purpose of BI is to get data on internal operations, on market competitors, and so on, and make justifiable decisions as opposed to just sitting in the bar and doing whatever comes to your mind. Now, data science is involved with this, except Really, there's no coding in BI. There's using apps that already exist. And the statistics in business intelligence tend to be very simple. They tend to be counts and percentages and ratios. And so it's simple. The light bulb is simple. It just does its one job. There's nothing super sophisticated there. Instead, the focus in business intelligence is on domain expertise and on really useful direct utility. It's simple, it's effective, and it provides insight. Now, one of the main associations with business intelligence is what are called dashboards or data dashboards. They look like this. It's a collection of charts and tables that go together to give you a very quick overview of what's going on in your business. And while a lot of data scientists may, let's say, look down their nose upon dashboards, I'll say this. Most of them are very well designed, and you can learn a huge amount about user interaction and the accessibility of information from dashboards. So really, where does data science come into this? What's the connection between data science and business intelligence? Well, data science can be useful to BI in terms of setting it up, identifying data sources, and creating or setting up the framework for something like a dashboard or a business intelligence system. Also, data science can be used to extend it. Data science can help get past the easy questions and the easy data to get the questions that are actually most useful to you, even if they require really sometimes data that's hard to wrangle and work with. And also, there's an interesting interaction here that goes the other way. Data science practitioners can learn a lot about design from good business intelligence applications. So I strongly encourage anybody in data science to look at them carefully and see what they can learn. In sum, business intelligence or BI is very goal-oriented. Data science perhaps prepares the data and sets up the form for business intelligence, but also data science can learn a lot about usability and accessibility from business intelligence. And so it's always worth taking a close look. Data science has a lot of really wonderful things about it, but it is important to consider some ethical issues. And I'll specifically call this do no harm in your data science projects. And for that, we can say thanks to Hippocrates, the guy who gave us the Hippocratic Oath of do no harm. Let's specifically talk about some of the important ethical issues very briefly that come up in data science. Number one is privacy. That data tells you a lot about people, and you need to be concerned about the confidentiality. If you have private information about people, their names, their social security numbers, their addresses, their credit scores, their health, that's private, that's confidential, and you shouldn't share that information unless they specifically gave you permission. Now, one of the reasons this presents a special challenge in data science, because we'll see later, a lot of the sources that are used in data science were not intended for sharing. If you scrape data from a website or from PDFs, you need to make sure that it's okay to do that, but it was originally created without the intention of sharing. So privacy is something that really falls upon the analyst to make sure they're doing it properly. Next is anonymity. One of the interesting things we find is that it's really not hard to identify people in data. If you have a little bit of GPS data and you know where a person was at 4 different points in time, you have about a 95% chance of knowing exactly who they are. You look at things like HIPAA, that's the Health Insurance Portability and Accountability Act. Before HIPAA, it was really easy to identify people from medical records. Since then, it has become much more difficult to identify people uniquely. That's an important thing for really people's well-being. And then also proprietary data. If you're working for a client, a company, and they give you their own data, that data may have identifiers. You may know who the people are and they're not anonymous anymore. So anonymity may or may not be there. Major efforts to make data anonymous. But really the primary thing is that even if you do know who they are, that you still maintain the privacy and confidentiality of the data. Next, there's the issue about copyright, where people try to lock down information. Now, just because something is on the web doesn't mean that you're allowed to use it. Scraping data from websites is a very common and a useful way of getting data for projects. You can get data from web pages, from PDFs, from images, from audio, from really a huge number of things. But again, the assumption that because it's on the web, it's okay to use it is not true. You always need to check copyright and make sure that it's acceptable for you to access that particular data. Next in our very ominous picture is data security. And the idea here is that when you go through all the effort to gather data, to clean it up and prepare for an analysis, you've created something that's very valuable to a lot of people. And you have to be concerned about hackers trying to come in and steal the data, especially if the data is not anonymous and it has identifiers in it. And so there is an additional burden placed on the analyst to ensure to the best of their ability that the data is safe and cannot be broken into and stolen. And that can include very simple things like a person who was on the project but is no longer, but took the data on a flash drive. You have to find ways to make sure that that can't happen as well. There's a lot of possibilities. It's tricky, but it's something that you have to consider thoroughly. Now, two other things that come up in terms of ethics, but don't usually get addressed in these conversations. Number one is potential bias. The idea here is that the algorithms or the formulas that are used in data science are only as neutral and bias-free as the rules and the data that they get. And so the idea here is that if you have rules that address something that is associated with, for instance, gender or age or race or economic standing, you might unintentionally be building in those factors, which, say, for instance, for Title IX, you're not supposed to. You might be building those into the system without being aware of it. And an algorithm has this sheen of objectivity, and people can say they can place confidence in it without realizing that it's replicating some of the prejudices that may happen in real life. Another issue is overconfidence. And the idea here is that analyses are limited simplifications. They have to be. That's just what they are. And because of this, you still need humans in the loop to help interpret and apply this. The problem is when people run an algorithm, they get out a number, say to 10 decimal places, and they say, this must be true, and treat it as written in stone, absolutely unshakable truth. When in fact, if the data were biased going in, if the algorithms were incomplete, if the sampling was not representative, you can have enormous problems and go down the wrong path with too much confidence in your own analyses. So once again, humility is in order when doing data science work. In sum, data science has enormous potential, but it also has significant risks involved in the projects. Part of the problem is that analyses can't be neutral, that you have to look at how the algorithms are associated with the preferences, prejudices, and biases of the people who made them. And what that means is that no matter what, good judgment is always vital to the quality and success of a data science project. Data science is a field that is strongly associated with its methods or procedures. In this section of videos, we're going to provide a brief overview of the methods that are used in data science. Now, just as a quick warning, in this section, things can get kind of technical, and that can cause some people to sort of freak out. But this course is a non-technical overview. The technical hands-on stuff is in the other courses. And it's really important to remember that tech is simply the means to doing data science. Insight, or the ability to find meaning in your data, that's the goal. Tech only helps you get there. And so we want to focus primarily on insight and the tools and the tech as they serve to further that goal. Now, there's a few general categories we're going to talk about, again, with an overview for each of these. The first one is sourcing or data sourcing, and that is how to get the data that goes into data science, the raw materials that you need. The second is coding. That again is computer programming that can be used to obtain and manipulate and analyze the data. After that, a tiny bit of math, and that is the mathematics behind data science methods that really form the foundations of the procedures. And then stats, the statistical methods that are frequently used to summarize and analyze data, especially as applied to data science. And then there's machine learning, ML. This is a collection of methods for finding clusters in the data, for predicting categories or scores on interesting outcomes. And even across these 5 things, even then, the presentations aren't too techie crunchy. They're basically still friendly. And really, that's the way it is. And so that is the overview of the overviews. In sum, we need to remember that data science includes tech, but data science is greater than tech. It's more than those procedures. And above all, that tech, while important to data science, is still simply a means to insight in data. The first step in discussing data science methods is to look at the methods of sourcing or getting data that's used in data science. You can think of this as getting the raw materials that go into your analyses. Now, you've got a few different choices when it comes to this in data science. You can use existing data. You can use something called data APIs. You can scrape web data, or you can make data. We'll talk about each of those very briefly in a non-technical manner. But right now, let me say something about existing data. This is data that already is at hand, and it might be in-house data. So if you work for a company, it might be your company records. Or you might have open data. For instance, many governments, many scientific organizations make their data available to the public. And then there's also third-party data. This is usually data that you buy from a vendor, but it exists and it's very easy to plug it in and go. You can also use APIs. Now that stands for Application Programming Interface. And this is something that allows various computer applications to communicate directly with each other. It's like phones for your computer programs. It's the most common way of getting web data, and the beautiful thing about it is it allows you to import that data directly into whatever program or application you're using to analyze the data. Next is scraping data, and this is where you want to use data that's on the web, but they don't have an existing API. And what that means is usually data that's in HTML, web tables and pages, maybe PDFs, and you can do this either with using specialized applications for scraping data, or you can do it in a programming language like R or Python and write the code to do the data scraping. Or another option is to make data, and this lets you get exactly what you need. You can be very specific and you can get what you need. You can do something like interviews, or you can do surveys, or you can do experiments. There's a lot of approaches. Most of them require some specialized training in terms of how to gather quality data. And that's actually important to remember, because no matter what method you use for getting or making new data, you need to remember this one little aphorism you may have heard from computer science. It goes by the name of GIGO. That actually stands for garbage in, garbage out. And it means if you have bad data that you're feeding into your system, you're not going to get anything worthwhile, any real insights out of it. Consequently, it's important to pay attention to metrics or methods for measuring and the meaning, exactly what it is that they tell you. There's a few ways you can do this. For instance, you can talk about business metrics. You can talk about KPIs, which means key performance indicators, also used in business settings, or SMART goals, which is a way of describing the goals that are actionable and timely and so on. You can also talk about, in a measurement sense, classification accuracy. And I'll discuss each of those in a little more detail in a later movie. But for right now, in sum, we can say this. Data sourcing is important because you need to get the raw materials for your analysis. The nice thing is there's many possible methods, many ways that you can use to get the data for data science. But no matter what you do, it's important to check the quality and the meaning of the data so you can get the most insight possible out of your project. The next step we need to talk about in data science methods is coding, and I'm going to give you a very brief non-technical overview of coding in data science. The idea here is that you're going to get in there and you are going to be king of the jungle, master of your domain, and make the data jump when you need it to jump. Now, if you remember when we talked about the data science Venn diagram at the beginning, coding's up here on the top left. And while we often think about sort of people typing lines of code, which is very frequent, it's more important to remember when we talk about coding or just computers in general, what we're really talking about here is any technology that lets you manipulate the data in the ways you need to perform the procedures you need to get the insight that you want out of your data. Now, there are three very general categories that we'll be discussing here on Data Lab. The first is apps. These are specialized applications or programs for working with data. The second is data, or specifically data formats. There are special formats for web data. I'll mention those in a moment. And then code. There are programming languages that give you full control over what the computer does and how you interact with the data. Let's take a look at each one very briefly. In terms of apps, there are spreadsheets like Excel or Google Sheets. These are the fundamental data tools of probably the majority of the world. There are specialized applications like Tableau for data visualization, or SPSS, a very common statistical package in the social sciences and in business. And one of my favorite, JASP, which is a free open source analog of SPSS, which actually I think is a lot easier to use and replicate research with. And there are tons of other choices. Now, in terms of web data, it's helpful to be familiar with things like HTML and XML and JSON and other formats that are used to encapsulate data on the web, because those are the things that you're going to have to be programming about to interact with when you get your data. And then there are actual coding languages. R is probably the most common, along with Python, a general purpose language, but it's been well adapted for data use. There's SQL, the structured query language for databases, and very basic languages like C and C++ and Java, which are used more in the back end of data science. And then there's Bash, the most common command line interface, and regular expressions. And we'll talk about all of these in other courses here at Data Lab. But remember this, tools are just tools. They're only one part of the entire data science process. They're a means to the end. And the end, the goal, is insight. You need to know where you're trying to go and then simply choose the tools that help you reach that particular goal. That's the most important thing. So, in sum, here's a few things. Number one, use your tools wisely. Remember, your questions need to drive the process, not the tools themselves. Also, I'll just mention that a few tools is usually enough. You can do an awful lot with Excel and R. And then the most important thing is focus on your goal and choose your tools and even your data to match the goal so you can get the most useful insights from your data. The next step in our discussion of data science methods is mathematics, and I'm going to give a very brief overview of the math involved in data science. Now, the important thing to remember is that math really forms the foundation of what we're going to do. If you go back to the data science Venn diagram, we've got stats up here in the right corner, but really it's math and stats, or quantitative ability in general. But we'll focus on the math part right here. And probably the most important question is how much math is enough to do what you need to do? Or to put it another way, why do you need math at all? Because you've got a computer to do it. Well, I can think of 3 reasons you don't want to rely on just the computer, but it's helpful to have some sound mathematical understanding. Here they are. Number 1, you need to know which procedures to use and why. So you have your question, you have your data, you need to have enough of an understanding to make an informed choice. That's not terribly difficult. 2, you need to know what to do when things don't work right. Sometimes you get impossible results. I know in statistics you can get a negative adjusted R squared. That's not supposed to happen. And it's good to know the mathematics that go into calculating that so you can understand how something apparently impossible can work. Or you're trying to do a factor analysis or principal component, you get a rotation that won't converge. It helps to understand what it is about the algorithm that's happening and why that won't work in that situation. And number 3, interestingly, some procedures, some math is easier and quicker to do by hand than by firing up the computer. And I'll show you a couple of examples in later videos where that can be the case. Now, fundamentally, there's a nice sort of analogy here. Math is to data science, as for instance, chemistry is to cooking.